So we had this fundamental theorem of subspaces. Of subspaces of a matrix, and it relates the different possible solutions of linear equations you can create with these matrices. So the theorem said that the null space of a matrix, so just a reminder, what's the null space? Is the all possible vectors which solve this equation. This space is same as the column space. When I write R of R, that means the column space of the transpose of A. So you just transpose the matrix and you get a different linear system. You take its columns. This is the column space. So all possible linear combinations, which is just the span of the column vectors. And then this is your column space, but you don't take this. You take the orthogonal complement of it. So whatever your column space is, so suppose this is that space, you take all those vectors which are orthogonal to it. The orthogonal complement, which is all vectors orthogonal to this your space, your subspace. So the theorem says that these two spaces are same. And you can also write it, replace A by A transpose. Then the null space of A transpose is same as the column space of A and its orthogonal complement. So what I want to do is just show you some examples of it. It's a kind of a very useful theorem because it helps you compute the null space if you know the column space, and helps you you can compute the null space using the column space and the other way around as well. So whatever is convenient, you can do that, and the other one you can conclude from this theorem. So these examples will also teach us, just give us a bit more practice of how to compute these column spaces and null spaces. So let's take this matrix and let's compute its column space. So it's just the linear combination, arbitrary linear combinations. So that's the span of these two vectors, the vectors which form its columns. Take the two column vectors, all the column vectors, which are in this case are only two, and the column vectors in this case live in R2. Vectors belong to R2 because they have two components, and you have two of them, and make this span, that is arbitrary combinations. So in this case, this span turns out to be, because the other one is 0, is just A to A. So all vectors of this form or this form. So I can say that the column space is spanned by this vector. So it's a one-dimensional space, one-dimensional subspace of R2. The column vectors live in R2, but the column space is just one-dimensional subspace of R2. Now, what is the orthogonal complement of it? Meant of RA. So now you are looking for all vectors so these are arbitrary vectors from your space, which is R2, which are orthogonal to all vectors in this space. So I just write an arbitrary vector and demand that this arbitrary vector is scalar product with the vectors in my subspace which are of this kind is 0. So that's the scalar product. If I write this as some arbitrary vector, and the vectors here if I write as V, so I'm demanding that the scalar product is 0, where this is an arbitrary vector from R2, and this is a generic vector and an arbitrary vector from this column space. So this gives me the condition that AX plus 2AY is 0. Now A is arbitrary, so I must have X plus 2Y is equal to 0. A is not equal to 0 because if A is 0, then this vector is just the 0 vector, which is orthogonal to everything. I'm looking for a general one-dimensional space, a general vector from this space. So A is arbitrary. So I must have X plus 2Y is equal to 0. So that means X is equal to minus 2Y. Therefore, vectors of the form like this. So I can write them like this, where X is arbitrary. So I can also write it as, because arbitrary numbers I'm writing as alpha beta, so let's just write it like this. So that means the orthogonal complement which is just this symbol is a one-dimensional space, and I should have expected that it would be a one-dimensional space because my original subspace was one-dimensional, and I know that if I take any subspace and take its orthogonal complement, then the sum of the dimensions of these two is equal to the dimension of the full space. So my full space is R2 and my subspace RA was one-dimensional, so its orthogonal complement also has to be one-dimensional. So the orthogonal complement is a one-dimensional space spanned by this vector 1 minus 2. Wait. I made a bit mistake because X is equal to minus 2Y. So this is not the vector. I should write it as X is minus 2Y. So if I take Y arbitrary, then X is minus 2Y. So I have 1 minus 2 1 minus 2, and over here 1 minus 2. And you can check very quickly. The original space was spanned by 1 and 2. And this is spanned by minus 2 and 1. And their scalar product of these two vectors in the respective bases of the two spaces give you 2 minus 2, 0. They are orthogonal. So if you multiply them with some numbers, everything you generate like that, it stays orthogonal. So that's the orthogonal subspace. Now let us look at the null space because I want to check that if it is equal to the null space generated by null space of A transpose. Now A transpose is because A was 1 2 0 0, so it's 1 0 2 0. And the null space is all those vectors which solve this. X is some xy, let's say x1, x2, so I'm solving this system, this homogeneous system. So this is the augmented matrix which I have to solve. This is already in reduced echelon form. So I have the solution in front of me. This equation, this line doesn't give me anything. This line tells me that x1 plus 2x2 is 0, or x1 is equal to minus 2x2. Therefore, the vectors are of this form: minus 2, beta, and beta. So if I put x2 as beta, then x1 is fixed. So there's one free variable, and then the other is fixed by choosing a value of that. One is free variable, so the other is computed by fixing one value of that free variable. So the vectors are of this form. So this is same as, so this is a subspace spanned by minus 2 1. But this is same space. This is same space which we found for this guy. So therefore, NAT is RA perpendicular. Similarly, we can verify that if I start with this, the column space of A transpose, this should turn out to be equal to the null space of A. If you don't want to deal with the null space of A transpose, you want to make a statement about null space of A, then you have to compute the row space of the A transpose. So A transpose is over here. Now A transpose is 1 0 2 0. So the column space of A transpose is arbitrary linear combinations of these guys. But I know that 1 0 and 2 0 are not linearly independent. So that means I can write one in terms of the other and remove that. The remaining one will still generate the space, the subspace. So I have 2 0 is equal to 2 times 1 0. So I can eliminate this from the spanning set, and span will not change. I will still get the same space. So therefore, this guy, it just becomes A plus 2A and so this is just A plus 2B 1 0. So this is just A plus 2B 1 0. And this you can write as another number. So alpha 1 0. So that means that this space is a one-dimensional space spanned by this vector, the unit vector 1 0. Now I know, so what would be then the orthogonal complement? Well, I know by intuition, I'm in two dimension, I have this space, then the orthogonal complement is spanned by this orthogonal unit vector, this one, 0, 1. But we can compute. So I'm looking for all vectors in R2. So they are of this form, which have 0 scalar product with vectors in RAT. So I compute the scalar product with the vectors in RAT, and vectors in RAT are of this form. So I get AX plus 0 is equal to 0. A is arbitrary, so X has to be 0. Or you can just check the basis vectors on basis vectors, and then the orthogonality on all the span follows from it. So this gives you X is equal to 0. So X is 0, but there's no condition on Y. So the vectors in the orthogonal complement are of this form. So it's a one-dimensional space spanned by these vectors, this vector 0, 1. And now I know from my theorem that the null space of A must be same. So it must be spanned by 0, 1. That means vectors of this form should solve A of x is equal to 0. So you can check. Let's compute the null space. You have, this is your matrix, and you're solving the homogeneous equation. So you put 0, 0 here. This gives you, if I multiply by -2 and add below, I get just 0, 0, 0. So it has x1. If I'm writing this x as x1, x2, and gives me x1 is equal to 0, this equation, first equation. The second equation doesn't have any information, but x2 is arbitrary. There's no condition on x2. So these vectors are of this form. So x2 is an arbitrary number. I can write it as beta. So again, same as RAT, orthogonal complement. And you can check that if I take this and act on a vector of this kind, I should get a 0. So you do get 0 plus 0, 0 plus 0, 0. And I could have multiplied it with any number, doesn't matter. I can have put A here, it still gives me 0. Now let's look at another example. This time we have this matrix. Now the column vectors, I want to compute the column space of A. So column space of A is the span of these column vectors. Span of these. Now these vectors, column vectors of A, live in R2. So this span would be a subspace of R2. But I know that these vectors live in R2 and R2, so it will be a subspace of R2. So at maximum, at most, the subspace can have 2 dimensions. That is when the subspace would be equal to R2 itself. Is equal to R2 itself. So I have R2, either I can have a subspace, which would be a line over here, one of the any infinite number of lines, or a 0, or the whole thing. There are no other possibilities. So at most, the subspace can have 2 dimensions. So that means in this span, I have 3 vectors. So these 3 vectors in R2 cannot be, we have done these theorems, these 3 vectors cannot be linearly independent. So they must be, the 3 vectors are linearly dependent in R2. Just because you have 3 and you have only 2-dimensional space, which you are working with. So one of them can be written as linear combination of the other two. And we can then eliminate it from the span, and the span will, from the spanning set, and the span will still give us the same space as the span of these three. So for example, I can write this guy 3, 4 as, I have to write it as a linear combination of these. I have to make a 4 here. The only possibility is, because there's a 0 here, I have to multiply the first vector with a 2. And then to get a 3 here, I have to multiply this one with a 1. So this linear combination gives me this vector. So I can eliminate it and only work with these two. But I should check if these two are linearly independent or not, because if they are not, then I can again eliminate. So the subspace, maybe I should write it. I can eliminate 3, 4 from the spanning set. And the subspace spanned by the rest would be still same, because you don't even need it in spanning, because whatever you span with this vector can also be spanned using these two, because whatever, when you multiply it with some number, that's just equal to taking this linear combination, which you can directly make using these vectors. So this is all what we have done many times. So I can eliminate it and just work with these two and try to span the space using these rest. But I should then again check that are these linearly independent. So the other ones left are left in the spanning set. For R of A, that's what I was doing. Check if they are linearly independent. So we're checking this and matching the lower component. The only possibility is C1 has to be 0, but once I put C1 equal to 0 to get this thing 0 here, I must have C2 equals to 0. So I must have both these constants equal to 0 to produce a 0 here. This means that they are indeed linearly independent. So I cannot eliminate further. So when I span using these two, but two vectors in R2, two linearly independent vectors, R2 give me a basis for R2, because 2 is the dimension of R2. So a span would be, span of these two would be the full R2, because they form a basis. So that so I figured out that R of A is actually R2. Then what would be the orthogonal complement? The only vector over here would be 0, 0. It's just one zero-dimensional space. You call it zero-dimensional. Only one vector is orthogonal to all the vectors in R2. Because R2 is the full space, there are no other vectors which have zero scalar product with every vector in R2. So an arbitrary vector in R2 is of this kind. And if I'm looking for some arbitrary vector xy which has zero scalar product with it, only possible if x is equal to y is equal to 0 for all a and b. So that's what I know, that Ra orthogonal complement is the zero vector. This means that the null space of A transpose should be 0, 0. There's only one vector here, only the zero vector. That means if I consider this guy, A transpose, which is 1, 3, 1, 2, 4, 0, and write this equation for it, the homogeneous equation for it. The only solution should be, this is telling me, using my theorem, because I know using my theorem, fundamental theorem, that these two guys must be same. So then I conclude that the only solution of this would be 0, 0, 0. Only trivial solution is possible. No non-trivial solutions will be there for this. That's computing the null space. So let's check it if it's true. So to compute the null space, I take my matrix and solve the homogeneous over here. Solve this homogeneous linear problem. And when I do that, minus 3 times added below, I get 0. Minus 6 plus 4 gives me minus 2. And minus 1 times first row added over here, minus 2. Then I can change these rows to 1 by dividing by minus half. And then I can just add this with a minus below. I get the echelon form, and I can then add above to get the reduced echelon form. Multiply by minus 2 and add above, you get this. So this equation has no information. This equation is telling me that x2 is 0, and the first equation is telling me that x1 is 0. So that means the only solution is 0, 0. By the way, this equation AT is equal to x. So I should not have written like this. This has only two components because AT is 3 by 2. So it acts on a 2-column vector. It's x on a 2-column vector. So it had only two components, x1 and x2. And those two components are equal to 0. So we have confirmed that NA of transpose is just this, and this is equal to RA orthogonal complement. So let's just, to finish this argument, finish these examples, just check the other part of this theorem. Check RAT orthogonal complement is equal to null space of A. Now, what is the RA of T? It's spanned by A transpose has only two column vectors, so it's spanned by those two vectors, which are 131 and 240. These two vectors. So they live in R3. So when they span a subspace of R3. So it would be a subspace of R3, and we want to know what subspace it would be. So since I have two of these, if they are linearly independent, then they will span a two-dimensional subspace. If they are linearly dependent, then I can eliminate one of them, and then I'll be left with only one, and I will span a one-dimensional subspace. But I cannot span the full R3 because I have only two of them over here. So let's check if they are linearly dependent. Well, they are clearly linearly independent because I can look and try to match these. They can never be matched. I have to check this, right? That a linear combination can be made which gives me 0. But to get a 0 here, I cannot cancel this one against anything over here because it's already 0. So this thing requires that C1 is 0. But once I put C1 equals 0, then all of these, the first two components become 0. And to get a 0 here, I must have C2 is equal to 0. So that's the only solution for this equation. So that means these guys are linearly independent. So therefore, R of AT is a two-dimensional subspace spanned by these two guys. And I can explicitly write it as an arbitrary linear combination of these two so something like this. And now I want to compute its orthogonal complement. So I have the column space of A transpose, and I want to compute the orthogonal complement. So I pick up arbitrary vectors. The orthogonal complement lives in the same space as the subspace whose orthogonal complement you are computing. So it's a subspace of R3. So orthogonal complement is some subspace of R3 again. And I know just from general knowledge and intuition that because I have a two-dimensional subspace, well, I know it from the theorem, which we did a lecture ago, that my R of AT is two-dimensional. So its orthogonal complement would be one-dimensional. It would be something like this. Because your subspace dimension of your any subspace, in this case it's a very special subspace, but dimension of any subspace plus the dimension of the orthogonal complement of that subspace is equal to the total dimension, which in our case is 3. So but I can check it. I pick an arbitrary vector, and the definition of the orthogonal complement is that should have 0 scalar product with vectors in your subspace. Now, what I can do, I have to look for vectors. I can do this, look for vectors which are perpendicular to both basis vectors for R of T. So I have this subspace, it had two basis vectors, which I know are 1, 3, 1, and the other one is 2, 4, 0. If I pick up those vectors which are perpendicular to both of them, both of these, then by linearity they will be perpendicular to, they're all linear combination. That means they will be perpendicular to the whole subspace spanned by these two vectors. So I can just check that I can just make sure that the vectors I'm picking up are perpendicular to the basis vectors, and the rest follows. So I demand this, that the vectors in the orthogonal complement are perpendicular. So this is the computing the scalar product to these guys. So this gives me the first vector, this should give me 0. So this gives me 2x plus 4y is 0. And the other condition that it's orthogonal to the other basis vector as well gives me x plus 3y plus z is equal to 0. So this gives me x is equal to minus 2y, and I put it here. So this becomes minus 2y plus 3y plus z is 0. So y plus z is 0. That means z is equal to minus y. So I can write everything in terms of y. So that means vectors are of this form in orthogonal complement are of the form you have y, x is equal to minus 2y, and z is equal to minus y, and y is some arbitrary number. Arbitrary numbers looks nice if I write it with some alpha, so that you do not confuse that y component is just an arbitrary number. So it's a one-dimensional space, as I was expecting. Spanned by this guy. And you can check this vector which you have got is perpendicular to these two, because that's how I got it. Now I can check. Well, first of all, from the theorem, I know that the null space of A has to be this one. generated by this, is spanned by this vector. All vectors of this form will solve the this equation. All vectors of this form will solve the homogeneous equation Ax is equal to 0. And A is a 2 by 3 vector, so X is a 3-column vector, and I'm saying that it will take this form. So we can check, since we are checking the theorem. This is our A, starting one. And I'm solving the homogeneous equation, so I have to compute the reduced echelon form of this augmented matrix. So minus 2 times the first row added to the second, it is 0, minus 6 plus 4, minus 2, minus 2 plus 0, minus 2, 0. And then I just make the pivot in the second row to be 1 by multiplying by minus half. And then I have to make this guy to bring it to the reduced echelon form. I can make this guy 0 by multiplying by minus 3 to the second row and adding above. So I get 0, minus 3 plus 1, minus 2, 0. So what are these two equations telling me? This is x1, x2, x3 in this solution. So it's saying that this equation is saying x2 plus x3 is 0. That means x3 is minus x2. And the first equation is saying x1 minus 2x3 is 0. So x1 is equal to 2x3. But I can replace this here to get x1 is equal to minus 2x2. Now I can take x2 to be arbitrary. So alpha, and then x1 and x3 will be computed in its term. That means all the vectors in the null space are of this form. x2 is alpha, x1 is minus 2 alpha, and x3 is minus alpha. So it is indeed what we expected. This is equal to, as we were hoping for. We can also check that it is indeed a null solution of the null equation, of the homogeneous equation, because if I take this matrix and multiply it with this guy or any multiple of it, gives me minus 2 plus 3 minus 1 is equal to 0, and then minus 4 plus 4 plus 0 is equal to 0. So it is indeed a non-trivial solution. Now there's a very interesting application of this theorem, which is called the least squares solution. So what do I mean by this least square solution? So if you're given a system, Ax is equal to B, and it's a m by n system, and m is greater than n. And suppose that m is way larger than n. Then what do you have? You have m rows and n columns. So you have these kind of column vectors, and you are making a linear combination of these by picking n of them. And we know that the solution will only exist if this B, which is given to you, lives in the space spanned by these column vectors. Even if these column vectors are all linearly independent, then you will get the biggest subspace of the live in Rm. You will get the biggest subspace of Rm. But if n is much less than m, you will still get, in the best case scenario, a very small subspace of Rn. An arbitrarily chosen vector over here, B, will not live in that, may not live in that subspace. In most cases, if you arbitrarily choose it or if someone gives it to you, it will not be in that subspace. So you have only some small subspace where these guys live, and this vector could be living anywhere else in the subspace. Unless it falls in that subspace, you will not have the solution. This is the one of the fundamental conditions for solutions to exist, that the linear combination of the columns of A is gives you this B. So as we had discussed, we do not expect a solution to exist when m is greater than n. Only for very special values of B you have a solution. But you can find an approximate solution. It's some sort of approximate. We will make it precise. What do I mean by it? Best case or nearest possible solution to this system. So it does not solve it, but it's very near to some kind of a solution which could have existed. And why would we need it? If it doesn't solve it, why do we need? If it doesn't solve it, why do we even care to get an approximate solution? Well, you may need this kind of approximate solution for many applications. So before we go and make it precise that what do I mean by this approximate solution, which will be called the least square solution, which will always exist. Let's first see why would we need it. So examples of where such a solution may be useful. So suppose you have two variables. Variables x and y. So demand and supply or something, y depends on x in some way. And you know, or you are told, someone tells you, or you model it to a linear relationship. And you know that there's a linear relationship between y and x. That means y is equal to y is proportional to x, and there may be offset like this. So y is linearly related to x. It's a relation which is known to you. Someone tells you that these two variables behave in this way. They're linearly related. Or you're just trying to model. You're given some data. There's a quantity x and there's a quantity y, and you want to find the relation between them. And you just try that perhaps for various reasons you believe that there's some kind of a linear relationship between them. So that means you are expecting the graph of this line. If I draw it like this, you're expecting something like this kind of relation. But and then you go and you try to measure different x1 and y1 experimentally, or you generate them. So you go in the field and you gather data for x and y, and you get some values. You plot them. They will never fall on this line which you are expecting them to follow for various reasons. First of all, in your experimental collection of data, there will always be some errors. When you have a law relating two variables, when you experimentally measure those variables, they don't fall exactly on that line. There's actually no meaning in saying that they are exactly on that line, because the points on that line are real numbers which you need to specify with arbitrary accuracy, and there's no such thing as arbitrary accuracy in the real world. So there will be a little bit offset depending on how accurate your data is, and there will be errors. No matter how careful you are, there will be some errors, and even if the errors are minimized, just because you are plotting some finite numbers, they will be not be exactly falling on this line. Then also, it may not be true that these two variables, you are just guessing, you are just making a model that these two variables are related to a line. So they may not be related exactly to lines. That's why they are offset. There's perhaps the real law is something like this, but you're modeling it with the line. So given the data, you want to find that what line best describes this data. What linear relationship best describes this data? So when you ask this question, you are looking for, so what line best describes the experimental data? So that is the question which is asking what is A and what is B. These two parameters for the line you are trying to find. And that will give you the law which describes the relationship between these two. So you're just told that it's a linear relationship, but you want to find what is A and what is B. So how would you do that? Well, you will have in your data these values. You measure x, you get x1, y1, a value of x1 and a value of y1. You measure for some other value of x2, you get another y2. Another value of x you measure, you get another value for y, and so on. So suppose you have up to m points in your data, and m is some number. So when you plot it, when you put this back in this equation, you have these kind of linear relations you are generating. A plus B, A and B are unknowns. You're trying to find them, but you are saying that when you put this data in, this is what you get. So you get this. So you generate n m equations. You have m equations. These equations, I can give them a matrix form. because I know that these polynomials give me some kind of a vector space. So I can get these equations by writing this. And wait, was I writing like this? Sorry. I should have called this. When I put this data up there, these are A's according to this. And these are B's. So then over here, I get this. So then I have over here a m by 2 matrix acting on a 2-column vector of unknowns and producing this m column vector. Now in general, there would not be a solution. Obviously, the solution will exist only if all of them lie exactly on this line, not otherwise. And that's a very unlikely situation. So in general, you expect that they will not lie on that line exactly. So a solution will not exist. But you want some kind of a best solution. And when you find that best fit over here, that will be a value, a best fit will give you the approximate solution, which in some sense is the best. And that will give you these parameters. Similarly, you could have probably modeling it with a linear equation. That's not necessary. So suppose you are told that the relation is quadratic. Could be any polynomial which you are told. So y is equal to ax square plus bx plus c. And you want to find, given the data, you're given this data, you have measured x and y a bunch of time, and this is your data. And you want to find that what kind of a graph, quadratic graph, with what values of a, b, and c will best describe, will best fit this data. So this time, again, what you have, you're given x1, you compute the squares, x1 square, that is just a computation. You just put in your calculator and compute the squares as well. And then you know that this is what you are expecting. That a x1 square plus b x1 plus c is equal to y1, because this is what you are expecting that the law says for all these numbers, for all pairs of x1 and y1. Up to the number of data points you have. these set of equations, then you can write as x1, x2, x3 up to xm, then x1 square, x2 square, x3 square up to xm square. Acting on, I have to produce this thing over here, so I better put C, because the way I have written this matrix, I could extend these rows, then I can write the A first, but since I have written this row first, so I should write CBA. These are the unknowns which I am trying to find. Again, no solution will in general exist, because this is a much bigger matrix and it's only a very small subspace which will solve it. And in any case, since I do not expect that whatever this law is, I do not expect this data to exactly lie on that line which is describing this data. Rather, I have experimental, observational inaccuracies which put this data away from that line. This line is just an approximate characterization of that data. So it's not gonna exactly follow. But I'm looking for a best fit for these data points. A solution does not exist because a solution will exist if these points were exactly on this line. But they are not. But a solution which is closest to this line will exist. So in a sense, I want to create those points which are closest to the subspace, which will be an exact solution. So that would be the best fit, which is also called, which I'm calling the quadratic least squares. Is just a name, probably a bit misleading. Least squares solution to this kind of linear system. So the solution doesn't exist, but a best fit kind of solution exists. Will give me the best values for the model, which are these A, B, C. So I want to find what are the values for A, B, C, which give me the model which best describes this data. So that would be the best fit solution, and how to find it, that will be in the next lecture. So I'm going to stop here.